This tutorial will be mainly walking through the main essential of OneAPI by looking at the vector add example. In order to get started, we need to get OneAPI sample from the GitHub repository, which is linked in the description below as well. So here we will download the code zips. Personally, I have already have the sample on the disk. I will open the vector add Visual Studio solution right now, just over here. The first question you may ask is, okay, so now I have the code, but how do I compile and run it? To compile and run a OneAPI or DPC++ code, there are two ways. One is directly through Visual Studio and the other one is through command line. If you wish to run this file through command line, make sure to refer to the Intel compilation guide linked in the description below. In this tutorial, we will be mainly showing compilation through Visual Studio. In order to do this, right-click on Solution Explorer, Rebuild. So we'll see it's building right now. And after it is compiled, we can hold Ctrl, Fn, and F5 to run this code. We see that it is by default using Intel integrated graphics over here. So, okay, now we know how to run the code. We'll now look into how the code works. Of course, the starting point is to go back to our main method right over here. In the very first few lines, it decides which device to select. Here we're using default selector, which is by default select the Intel graphics on my device, as we have seen before. So on my device, I have Intel UHD graphics card, a default Intel graphic card as mentioned before, a CPU, and an FPGA emulator. Of course, I also have NVIDIA graphics, but OneAPI currently does not support offloading kernels to NVIDIA graphics card. So OneAPI provides several selectors by default. It includes default selector, CPU selector, GPU selector, and accelerator selector. So on my device, CPU selector corresponds to Intel i9 CPU, and GPU selector corresponds to the default one we have seen before, and accelerator selector corresponds to the FPGA emulator. But as I've mentioned before, I also have a UHD, but none of the default option provides a selected UHD device. So let's say I want to let my UHD graphics run vector addition. What should I do? So in this case, we need to write an additional or custom device selector, which I will show you right now. In general, we write custom device selector not to just use something that's not provided by the default, but it is usually used when we want to balance the load on each device. So let's say your GPU is already running at full load. It does not make sense to continue submitting kernels to that device. We will call our custom selector as UHD selector, which I will define a class right about. Just put in what I had before. And here you need to override the base class, which is device selector. Every default selector that was provided by OneAPI is also overriding this class. In general, all we need to do is after we inherit the class is to override the operator method, and that returns score for each device according to our need. The device with highest score will be chosen in this case. So in this case, it is UHD because I'm explicitly finding a UHD in the name of the device, and that will return 100 score. We can also print the name of the device just to see what options are available on the device. So after this is done, we can switch the default selector to the UHD selector. let's recompile and run the code again. Okay, here. So we have mainly for device, graphics, UHD, CPU, i9, and FPGA emulator. And currently we're running on the UHD graphics, which is exactly what we need. Okay, so now the device is set, and now let's move on to the initialization of shared vector. So here we're allocating memory for universally shared. It's a universally shared memory for the vector. By universally shared memories, which is shortened to USM, it is a memory that both host and the device can access. What I mean by host is, for example, in this case, the CPU, and the device is the GPU. Now moving on to submitting kernels. Here, after the arrays or vectors are initialized, it is defined in this vector add function. Here we're using parallel for with number of item, which is the size of the vector, and that is the number of work items as well. So now we're dividing array into n work items, where you can see each work item as a thread, and each of them execute the same kernel function body, which in this case is this one, independently. Those work items maps to hardware during runtime. After this is submitted and kernel is destroyed, the result will be written back to the host. But this is a simple example of a single kernel. So suppose you're submitting multiple kernels. The API will intelligently decide which kernels to run in parallel and which ones do not. Let's look at an example here. So let's say you're submitting 4 kernels. The first one writes to A, the second one writes to A, third one writes to B, and the fourth one read from A and read write to B. So the kernel graph or data dependence graph can be constructed like this. Since kernel A is writing to A, and then the next kernel that is also writing to A may probably depend on that first kernel. There's a dependency over there. And then once you look at kernel 4, which is using both A and B, then that kernel 4 is dependent on the closest kernel that writes to A and the closest kernel that writes to B. So after this graph is constructed, you can see that kernel 1 and 3 or kernel 2 and 3 can be run at the same time, so that there are in total a depth of 3. Alright, back to code. So this function is then waiting for the kernel to complete. After all the results are computed, we can then verify it by comparing to the simple or sequential version. As we have seen from the previous output, it is indeed equal and successful. After all of the operations are done, make sure to free all the dynamically allocated memory. And yeah, that's it. If you have questions, make sure to leave a comment below.